Hello students and welcome to the 59th lecture on particle physics. And today we shall be talking about accelerators. I will give you an idea about the different accelerators in very brief, and then you can read it from any book or even on the internet. These materials are available readily. The important point is, why do we use them? The answer to that is, there's not a single purpose for which we use. There are many applications of these accelerators in medical sciences, in condensed matter, in industries, and then of course they have been developed by physicists, and therefore that means they are useful for us, for the particle physicists, for the nuclear physicists, and in the other branches of physics. Now, what do? We want to accelerate the particles, and then that means if you recall from my basic lecture, I told you from de Broglie hypothesis that lambda is of the order of h upon p, and that means this is proportional to 1 over e, and that means if I increase the energy of the projectile, then the wavelength will be smaller, and then we can go inside of an object. This is what we have seen, that is starting from 120 years ago till now. We have, starting from a few kVs of energy, we had MeVs, we have GeVs of energy, and today we are talking about 7 trillion electron volt and 7 trillion electron volt collider at Large Hadron, that is known as Large Hadron Collider at CERN. Now, the important point is that all these accelerators which we talk about, they are not of the same time. And we are going to discuss about the cyclotron, the linear accelerators, the colliders, the storage ring, and synchrotrons in very brief. Now, the important point is that what are accelerators? They are used to accelerate charged particles such as electrons, protons, or ions to very high speed and energies. These accelerated particles are then used for various purposes, including fundamental research in particle physics, material science, medical diagnostics, and cancer treatment. Particle accelerators come in different types and sizes, each with its own unique characteristics and applications. Here is how a particle accelerator works and why it is important. Basic principle: particle accelerators use electromagnetic fields to propel charged particles along a defined path, because electric field, the difference in the potential, will give them acceleration, and then the magnetic field perpendicular to it will allow them to move in a particular direction. Therefore, to collimate the charged particles, we use magnetic field, and then to accelerate them, we use the electric field. We cross them through different potentials. By applying electric fields to accelerate the particles and magnetic fields to control their trajectories, accelerators can increase the particles' speeds and energies. There are several methods for accelerating particles in an accelerator. Electrostatic accelerations: they use static electric fields to accelerate particles. Linear accelerators: particles are accelerated in a straight line by a series of electric fields. Then you have circular acceleration. Here particles are accelerated in a circular path by applying magnetic fields, allowing them to pass through same acceleration region multiple times. Now, basic concept is, suppose we want to accelerate a charged particle by allowing it to move through a potential difference. I have taken a very simple case of 12th class. Now, for instance, take a charge and place it inside a parallel plate capacitor. We will assume the capacitor has a uniform electric field E, and a potential difference with a magnitude that will have is the distance between the plates is d. Delta V will be E into d, where is the d is the distance between the plates. Now, a positive charge released from beside the positive plate will accelerate towards the negative plate. Say this is the positive charge, these are the negative charges. Similarly, a negative charge released from near the negative plate will accelerate across the gap and leave the parallel plates at high speeds. Gain in kinetic energy will be half mv square, and that will be nothing but the charge of the particle times the potential difference through which it has passed through. For example, I have taken a very simple case. A charged particle is accelerated through a potential difference, for example, of 12 kilovolts and acquires a speed of 10 power 6 meter per second. It is then injected perpendicularly into a magnetic field of a strength 0.2 Tesla. Find the radius of the circle described by it. What I have promised you, that this is a 12th class physics. Therefore, delta V is equal to ED, and the force acting on the charged particle will be QE, and that will be simply from here Q delta V by D. Now the work done will be the change in kinetic energy, and therefore W will be equal to force times the distance the particle has moved, and that should be equal to the kinetic energy gained by the particle. Therefore, from here you can write Q by M as equal to U square by twice delta V. Now once you have Q by M as U square by twice delta V, then if you are applying a magnetic field which is perpendicular to it, and because of that the charged particle is following a circular path, and say the radius of the circular path is R, then that means centripetal force, that is equal to mu square by R, must be equal to QUB, and that is equal to, from here we can obtain Q by M is equal to U by BR, and then we compare these two. U square by twice delta V is equal to U by BR. We evaluate the radius of the circular path, and this will turn out to be about 12 centimeters. Therefore, the important point is that if you are having a high speed, or in other words, if you have a collider machine of 27 kilometers circumference, or a collider machine of 10 kilometers circumference with the same magnetic field and the electric field, then you can see that what will be the radius of the path. Therefore, the important point is the radius of the path, the applied magnetic field, and the kinetic energy gained by the particle, and what potential it is passing through. These are all related. As you can see that Q by M, charge to mass ratio, depending upon the speed of the particle and the potential difference through which it is passing. Then we are seeing that this Q by M is also related to the magnetic field and the radius of this circular path which it is making. Therefore, these are the important concepts to understand the acceleration of charged particles. Now let us talk about first the linear accelerators. These accelerate particles in a straight line. Circular accelerators, these accelerate particles in circular path. Examples include cyclotrons, synchrotrons, etc. Then you have colliders, like you have Large Hadron Collider at CERN, accelerate two beams of particles to high energies and collide them head on. Examples include Large Hadron Collider. Then you have fixed target accelerators. They accelerate particles to high energies and direct them onto a stationary target for experiments. A stationary target means I am talking about the laboratory frame of reference, where target is at rest, the target's energy is rest mass. Now let us talk about the cyclotron. A cyclotron is a type of particle accelerator used to accelerate charged particles, typically protons or ions, to high speed for various applications in nuclear physics, medical imaging, and particle therapy. The operation of cyclotron involves the principles of electromagnetism and classical mechanics and can be described as follows. Basic principle. A cyclotron accelerates charged particles by subjecting them to a combination of electric and magnetic fields within a circular vacuum chamber. The source of particles, the process begins with a source of charged particles, often a small amount of ionized gas or a beam of charged particles injected into the vacuum chamber. Then you apply alternating electric fields. Within the vacuum chamber, two hollow D-shaped electrodes called Ds of this shape are placed facing each other. These Ds are connected to an alternating power supply. As the polarity of the electric field alternates, it causes the charged particle to accelerate back and forth. Therefore, this is how it moves. And then if you, depending upon the size of the D and what kinetic energy you want, accordingly when you achieve this, the radius path, then you take this beam out. Magnetic field, a strong magnetic field is applied perpendicular to the plane of the Ds so that it can move along the plane. This magnetic field causes the charged particle to experience a Lorentz force perpendicular to both their velocity and the magnetic field direction. This force bends the path of the particles into a circular trajectory. Now here the most important thing is the synchronization. The frequency of the alternating electric field is synchronized with the orbital frequency of the charged particles in the magnetic field. As a result, the particles gain kinetic energy with each revolution. Therefore, the important point is the polarity has to change as the particle reaches here. When this will become of opposite polarity, the particle will be accelerated towards this. Then define a path. When it will come to this point, the polarity now of this will get reversed. Therefore, this synchronization is a very important concept in the case of cyclotron. Now, the energy gain as the charged particle accelerate through each half circle, they experience a gain in kinetic energy due to the electric field. This energy gain causes them to move in a larger orbit with a higher velocity. And once you have reached the desired kinetic energy, then you try to extract that particle. Once the particle reaches the desired energy level, they can be extracted from the cyclotron for various applications that we have talked about. Therefore, this is how we are talking about. These are the two Ds through which the particle is traversing, and then you are applying a perpendicular magnetic field so that the path of the orbit of this projectile or the particle which you are accelerating is circular. Now, generally what happens, one takes, for example, hydrogen atom, and then first one knocks out the electron such that your hydrogen atom becomes ionized, and ionized hydrogen atom is nothing but a proton. Therefore, this is how you have a proton source, and then you are placing it between the two Ds, and through the alternating frequencies you are forcing the proton to move along the two Ds, and applying the perpendicular magnetic field, you are forcing the proton to follow a circular path. Therefore, the example which I had given to you, the same example, how they gain energy, or what should be the radius of the orbit, or that will depend upon how much you want to have the energy, because you know we talked about Q by M. Therefore, you know the charge of the proton, you know the mass of the proton. Then you have seen that this ratio depends upon the radius of the circular path and the applied magnetic field. And then you have the Q by M also related to the difference, the potential between the two plates. And this is how you accelerate the particles. Then you have linear accelerators. It is also known as LINAC. Is a type of particle accelerators that accelerates charged particles such as electrons, protons, or ions along a straight path. Unlike cyclotrons, which are circular paths, linear accelerators propel particles in a straight line. Here is how a linear accelerator functions. First, you have an electron gun, for example. The process begins with an electron gun which generates a stream of electrons. The electrons are typically emitted from a heated cathode, for example, and accelerated towards the anode by applying an electric field. Then you have radio frequency cavities. These cavities are used to accelerate electron these accelerated electrons they enter the radio frequency cavities or waveguides. These cavities are arranged along the accelerator's path and are powered by radio frequency generator. As the electrons pass through the radio frequency cavity, they interact with the alternating electric fields produced by the radio frequency generator. These electric fields provides additional energy to the electrons, accelerating them to higher speeds. Then you use magnets to not allow the electrons to move out. As you can see that if you switch on the torch, then the lights spread. Okay, to focus those electrons, you again apply here also the magnetic field, and this is you apply to force the electrons to follow the straight path. While mind it, when we were talking about cyclotrons, we force the charged particle to follow the circular path. Here we are forcing them to follow a straight path. That means for collimation, we are using the magnetic field. Now, along the accelerator path, the electron beam may be collimated or shaped using collimators and other devices to ensure that it remains focused and uniform. Then once you have the desired energy of the electron or proton or whatever you like, then if with that desired energy, you bombard that on a target and you achieve your desired result. Therefore, depending on the application, the accelerated electron beam may be directed towards a final target. For example, in medical linear accelerator used for radiation therapy, the electrons may be directed at a target material to produce X-rays for cancer treatment. The accelerated particles or radiation produced by the LINAC are then directed to the desired location for use in scientific experiments, medical applications, or industrial applications. Therefore, this is the simple picture of LINAC, and you can see that if the longer you will make these electrons to pass through, the greater kinetic energy that you will achieve, and this is what is generally done. As you can see, if the electrons are passing through the various electric fields and they are getting accelerated, then you will achieve more and more kinetic energy for the particle. Now, this is how these linear accelerators look. They are really very beautiful they look very beautiful in the laboratory. Now, then we come to the colliders. As I have told you that in the colliders, the two particles get smashed. Okay, they come from the different directions and then collision takes place, or then the scattering takes place. Therefore, both have got energy and momentum. And in all these are not one step process. They are different step processes. You achieve up to certain amount of energy through one accelerator, then you use another one, then you use third one, and so on. This is even at LSC, it is not that one accelerator is giving you 7 trillion electron volts of proton. Therefore, in a collider, it is a type of particle accelerator designed to collide beams of subatomic particles at very high energies. These collisions allows scientists to study the fundamental constituents of matter and forces that govern their interactions. Mind it, when you have huge amount of energy, then you will be able to see new particles, exotic particles, or your wavelength is becoming very small. Then you are going inside of a particle. You are seeing inside of an object. A collider consists of two accelerator structure with vacuum pipes, magnets, and RF cavities in which two beams of particles travel in the opposite direction. They can be two protons, proton-antiprotons, electron-positrons, electron-proton, nuclei. For example, at LSC, you have the lead-lead collision also. Or you can have electron-positron collision. Remember, when I was talking about SLAC experiment which discovered J by psi. Therefore, electron and positrons were coming from the opposite direction. Therefore, they can be these two particles can be of the same nature, or one can be particle and another can be antiparticle, or so on. Here is how they work and why they are important. Colliders accelerate beams of charged particles such as protons or electrons to extremely high speed using electric and magnetic fields. These particles are typically injected into a circular or linear accelerators and accelerated to energies close to the speed of light. Once the particles reach their desired energy, they are brought into collision with another beam of particles traveling in the opposite direction. The beams are focused and guided to interact at a specific point within a detector apparatus. When the particles collide, they release a tremendous amount of energy, which can lead to the creation of new particles or the transformation of existing particles. These interactions are recorded by detectors, as I have told you that we have at LSC, CMS detector, Atlas detector, Alice detectors, and various other detectors. Therefore, once the collision has taken place, new particles have been created and energy has been created. You want to study them, and this is for that you have to place the detectors. Now, sophisticated detector systems are used to measure the properties of the particles produced in the collisions. These detectors can identify various types of particles, measure their energies, momenta, and other characteristics, and reconstruct the processes that occur during the collisions. That means if the particle is passing through the path, from the length of the path, you can measure, tell us about its momentum, or depending upon if you are placing in the magnetic field, depending upon its curvature, you can tell us many more things. Therefore, experimental confirmation, many groundbreaking discoveries in particle physics have been made at colliders, including the discovery of Higgs bosons. These discoveries help to confirm and refine our understanding of the fundamental laws of physics. Therefore, this is a look of a colliding beam experiment, and this is how you are accelerating a particle in one direction, and then you have from the opposite direction, and then you are talking about the collision that is taking place. Therefore, this is what is 27 kilometer circumference, and you see the line which is showing here. We have the accelerators, and then we have placed the detectors at various places to where the collision will take place, and you will observe new particles, exotic particles, or you want to see the QGP signals and many more things. Now, what I have told you, that here we are talking about a 27 kilometer circumference. Now, if you want to achieve more energy, then your circumference should be really very large, and future circular collider may look something like this. Or if someone comes out with a very new technology, a new out of box idea, then also perhaps we can have more energy. Then we have a storage ring. In particle physics, a storage ring is a type of particle accelerators designed to store and circulate beams of charged particles such as electrons or positrons for extended period of time. Unlike colliders, which collide beam of particles head on, storage rings maintain beams in a closed loop, allowing particles to circulate continuously at high energies. The two rings intercept each other at few positions along the circumference. The faces of the benches circulating in the two rings are adjusted to make them meet at intersections. Here is how storage rings work and their significance in particle physics. The process begins with injecting charged particles into the storage ring. These particles are typically accelerated to high energies before being injected into the ring. This acceleration is achieved using pre-accelerators such as linear accelerators or synchrotrons. Then you apply magnetic field. Once inside the storage ring, the charged particles are kept in a circular path by strong magnetic fields produced by magnets positioned around the ring. These magnets bend the trajectory of the particles, causing them to follow a circular path. Then you use RF cavities to accelerate the particles to compensate for energy losses to synchrotron radiation and to maintain the particle at the desired energy level, storage rings often include radio frequency cavities. These cavities provide additional energy to the particles at specific locations around the ring, ensuring that they remain at the desired energy. Storage and circulation. Once the particles are circulated within the ring, they are continued to do so indefinitely. The particles maintain their high energies as they circulate, allowing for long observation times and repeated interactions with detectors. Storage rings are often equipped with experimental facilities located around the ring. These facilities include detectors and instrumentation designed to measure the properties of the circulating particles or to perform experiments that required the high energy particle beams provided by the storage ring. Storage rings have a wide range of applications in fundamental research, material science, and various other fields. They are used to study the properties of subatomic particles, to investigate the structure of matter, and to perform experiments in nuclear and atomic physics. They are also used in synchrotron radiation facilities to generate intense beam of X-rays and other types of radiation for use in research, medical imaging, and industrial applications. This is how a storage ring looks like, and this is why you have the RF cavity that because of the radiation loss, to compensate that, RF cavities are put, and this is how a proton storage ring at CERN looks like. Then we have synchrotrons. Using this, a charged particle such as electron or proton or a heavy ion particle such as gold ion is accelerated to very high energies in the presence of an alternating electric field while confined to a constant circular orbit by a magnetic field. The magnetic field serves to bend or deflect the path of the charged particles in order to maintain a constant trajectory within the cyclic accelerator. The magnetic field must gradually increase in strength as the particle's momentum increases. In addition, the frequency of the accelerating electric field must be maintained or adjusted as necessary in order to be synchronous with the orbital frequency of the charged particle. This is very similar to what we are discussing about the cyclotrons. The synchrotron is useful when the particle is accelerated to a speed approaching the speed of light, as in the acceleration of electrons or protons to extremely high energies, since under such conditions, speed changes only slowly as the energy changes. The beam pipe runs inside the gap of dipole moment magnets forming a ring. Say the orbit of a particle of momentum p in the magnetic field B has a circumference of radius r, then the equation of motion is dp by dt, that is equal to qv cross b, Lorentz force. If the Lorentz factor is gamma, then you can see that this will be gamma m dv by dt. This will be simply qv cross b. Then the centimeter acceleration, this will be dv by dt is equal to qvb upon gamma m, and that will be equal to v square by r, as we have discussed it in the very first problem that we talked about. And then the momentum will be simply from here will be qbr, and this implies if we multiply both sides by c, pc will be equal to qcbr. Therefore, if pc is measured in GV, b in Tesla, and r in meters, then you can write this PCV is in GV, and to have the proper units, you see this P momentum in GV, in natural units we are talking about, we are not writing C. P in GV means we are talking about natural units. This is 0.3 times the magnetic field that you are applying in Tesla, R in meters in natural units. Therefore, depending upon this, your energy of the particle is increased. This is how in synchrotron we achieve large amount of energy. Therefore, we have cyclotron, synchrotron, linear accelerator, we have storage rings, we have colliders, etc. to accelerate particles and to achieve the desired energy. If we want to have fixed target experiments, then we have a linear accelerators which is following a straight path, and then we have a target. If we want to get great energy, a huge amount of energy, then we are take the particles from the two directions and then we make them collide to achieve the desired result, to have exotic particles, new particles, to have radiations in the final state and all that. Now, once we have these accelerators, we have the events, and those events are detected by the different detectors. In our last lecture, we shall talk about these detectors, the qualitative features of these detectors. We won't go into the quantitative details because they are there in literature. Just we will talk about the historically from where we had started, from cloud chamber, bubble chamber, etc., GM counter, and then finally the semiconductor and sophisticated detectors. Let us stop here. Thank you very much.